This is the last part of chapter 3. I know this is a long chapter. There's a lot of different problems. And actually, this is the only chapter this unit test will be on because there's so many different problems. So once we get done with this one, we're done with this chapter and then it's time to study for your next test. All right, so we talked about stoichiometry and it's comparing what you start with, what you end with. You know, if I have so many grams of a reactant, how much product can I produce? And this is very important in industry because you need to have a product produced that's part of your job or part of your company. So this is a way of you can checking on that. So limited reactant is when you react two things together, which one do you run out of first? Okay, some simple. Say you're making ham sandwiches. You know you need 2 pieces of bread for every 1 piece of ham. Let's say you have 12 pieces of bread and you have 8 pieces of ham. Well, my limited reactant is going to be bread because I'm going to run out of bread. I'm going to take my 2 pieces of bread and to make sandwiches, and I put my 1 piece of ham. Well, after 6, I'm done. I'm out of bread, but I still have 2 pieces of ham left over. So they say bread is your limited reactant. It limits how many ham sandwiches you can make, how much product, and your ham is your excess reactant. That's what you have over. Me, I just throw a couple extra pieces of ham on the sandwiches, or just eat the ham, but you know how that goes. But that's an example of limited reactant, a simple example. So I'm going to show you, basically, you compare one reactant to the other and figure out which one you run out of first. Okay? All right, so limited reactant is the reactant present in the smallest amount. In other words, again, the one you run out of first. Here they have an example. We're reacting hydrogen and oxygen. We're going to make water. Okay, when we're done, the hydrogen's all done reacting. We got some oxygen left over. Okay, there's not enough hydrogen for it to react with, so you end up with extra oxygen. So oxygen is what they call your excess reactant, and hydrogen's your limited reactant. The hydrogen limits how many water molecules you can make, because once the hydrogen's gone, your reaction stops. Okay, again, in this example, oxygen would be your excess reactant because you have some left over. Okay, it didn't get reacted because you ran out of hydrogen. So hydrogen's your limited reactant, oxygen's your excess reactant. Okay, so here's an example. We're going to talk about a limited reactant, and this is a super important reaction in industry. It's when they make ammonia. Ammonia is huge in farming, fertilizers, all kinds of stuff. They use a lot. And all they do is called the Haber process. And what they do is they take nitrogen and hydrogen, they react them together, and you get ammonia. And the first thing you have to do all stoichiometry problems is you have to have a balanced equation. Because remember, a balanced equation is where we get our mole ratios. Okay? So here we have our mole ratios. Okay? How many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2? So in other words, I know the amount of each of my reactants. I know that I have 3 moles of nitrogen and I have 6 moles of hydrogen. And I want to know how much product I'm going to produce. Well, before I can figure that out, what I need to do is I need to figure out which one of these I run out of first. Okay? So you compare one to the other. You pick one, it doesn't matter which one you do, you're going to get the same answer anyway. So to find my limited reactant, what I'm going to do is I'm going to take my 3 moles of nitrogen and I'm just going to do a mole ratio. I'm going to put moles of nitrogen on the bottom, what I'm trying to get rid of, and moles of hydrogen, what I'm trying to find on top. And this number, this 3 and this 1 comes from my balanced equation. It's my mole ratio. And that gives me 9 moles. Okay, so when I have 3 moles of nitrogen, I need 9 moles of hydrogen. I only have 6 moles. So I need 9 moles, I only have 6. So hydrogen is my limited reactant. I run out of hydrogen before I run out of nitrogen. If I was looking at this reactant and I wanted to produce more product, I would have to add more hydrogen. If I had more nitrogen, I'm still not going to get any more product because the hydrogen's the one I run out of first. Okay? So now that I know which one's my limited reactant, that's what I start with. I start with my 6 moles of hydrogen. And now I do a mole ratio of my product, what I'm trying to find. Moles are what I'm trying to get rid of on the bottom. Moles are what I'm trying to find on top. Put that on top. And I end up with 4 moles. So when I react these two together, I end up with 4 moles of NH3. If I would have started with my moles of nitrogen, I would have ended up with more moles of product. And then if you actually did it, I'm like, why don't I have 4 moles of Ammonium. Well, when I did my calculation, I didn't start with my limited reactant. You always start with your limited reactant, okay? Okay, calculating the amount. Again, here's another limited reactant. Okay, one of a common reaction we talk about all the time is hydrogen and oxygen producing water. This happens in hydrogen fuel cells. If you have a hybrid car, it happens there. Okay, suppose you have 150 grams of hydrogen and 1,500 grams of oxygen. How many grams of water can you form? Again, the first thing I got to do is, do I run out of hydrogen or do I run out of oxygen? Which one do I run out of first? So I do a limited reactant. So I pick one reactant and compare it to the other. Okay, let's say I pick the 150 grams of hydrogen. And again, you can do the 1,500 grams of oxygen. You're still going to get the same limited reactant. It doesn't matter. So I'd take 150 grams of hydrogen. Okay, 1 mole of hydrogen. This is the mass of H2. Remember, when you do hydrogen, it's H2, so you have to write it as 2 grams, not just 1. Okay, so now what I did was I got rid of grams and I got moles. Then I do my mole-mole ratio, put moles what I'm trying to get rid of, hydrogen on the bottom, moles of what I'm trying to find on top, oxygen. Okay, and then I switch it now to grams of oxygen. I got 32 grams, and again, oxygen's O2, so oxygen's 16, but there's 2 of them, that's 32. That's where I get that from, in 1 mole. So I multiply and I divide and I get 1,200 grams of oxygen. What this tells me is when I have 150 grams of hydrogen, I need 1,200 grams of oxygen. This is what I need. Okay, I have 1,500. So since I have more than I need, hydrogen's my limited reactant. It's the one I run out of first. Okay, then if I want to figure out my product, all I have to do is start with my limited reactant, 150 grams, get rid of grams of hydrogen, 1 mole, 2 grams, do my mole ratio. In this case, it's 2 moles of hydrogen to 2 moles of water. It works out to be the same because if you look at my balanced equation, 2's and 2's. Okay, and then I change it to grams. 18 is the mass of water. That's 2 hydrogen, 1 oxygen added together. So when I multiply this, I get 675 grams of water. So if I take 150 grams of hydrogen and 1,500 grams of oxygen, well, I'm going to waste oxygen. I'm going to have 300 grams left over. But what I'll end up with is this. Now, if I started with the 1,500 grams of oxygen, this number would be a lot larger. Basically, I'd be lying because there's no way I can produce that because I don't run out of oxygen. I run out of hydrogen. Okay. Then I did another one, and what I did instead of, like I did ones over, well, I'll show it to you. Maybe this will look better to you, maybe. Okay. If you have 15 grams of copper chloride and 20 grams of sodium nitrate, which one's the limiting? Well, first thing you have to have is a balanced equation. You cannot do stoichiometry without it. Okay, and then you pick one. And it doesn't matter if I start with this one or this one. You're going to get the same. Okay, let's say I started with the 20 grams and I wrote it out this way instead of the slashes. Maybe this is easier for you to read. I don't know. But again, I got 20 grams of NaNO3. I put 1 mole here, and this is the mass of sodium nitrate. This is 1 sodium, 1 nitrogen, and 4 oxygen added together. And again, you can get this number on the app on your phone. So all I did so far was get rid of grams of NaO3. Now I have mass. This is my mole ratio. This is where I need my balanced equation. This is the only place you need your balanced equation, okay? So I put 2 moles here and 1 mole here. Why? Because I got a 2 here and nothing here, which is 1. So now what I did is I switched from moles of NaNO3 to moles of CuCl2. My last step, I got to change this to grams. Okay, so I put 1 mole here and 134.5, that's the mass of this. Okay, so I take 20 times 134.5 divided by 85 divided by 2, and I get 15.8 grams of copper 2 chloride. That's how much I need. Okay, I need 15.8. I only have 15. I don't have enough. I'm a little short. It's not a lot, but I'm a little short. So my limited reactant is copper 2 chloride. I run out of that before I run out of sodium nitrate. Again, if you add more sodium nitrate, you're not going to produce any more product. Okay? If you want to calculate the product formed after finding the limited reactant, you need to start with the limited reactant. Always start with that. Oh, I lost my E here. This case would be 15 grams of copper 2 chloride. Always start with your limited reactant. Okay? The other thing we do is something called theoretical yield. Okay, when we calculate on paper the mass, like if you start with this many grams of product, reactant, how much product? On paper, that is the calculated amount. It's called the theoretical yield. And you never get it. We always mess up a little, lose a little bit, okay? But You can actually, when you do an experiment, you can figure out how well you did by something called calculating your percent yield. And in the percent yield, you need two things. You need your theoretical yield, and that's what you get from paper when you write it all down. And then the actual yield, that's when you do the experiment, how much do you actually end up with, okay? So you have the actual yield is when you do the experiment and you measure your product. The theoretical yield is what you get on paper. And we compare the two of them. And again, it's a way to see, did I do a very good job? You want to be close to 100%. You can't be over 100%. If you're over 100%, you divided wrong because you can't make something out of nothing. So you can't have more than 100. Okay. So percent yield, you find by comparing the actual, what you got, to the theoretical, what you should have got. Okay. And there's the formula. And then you multiply by 100 to change it to percent. All right. So here's an example of a problem. What we're trying to do is we're going to compare. We're going to start with the reactant, and we're going to figure out what we should get for the product, and then I'll show you how to do percent yield. It's actually on this page. Okay, so I start with my grams of, I think it's acetic acid or something like that. 1 mole, this is its mass. I do my mole ratio, and then this is the mass of this product. So I take 25. I'm not going to multiply by 2 and divide by 2. I'm just going to take 25 times 146 and divide by 84. Okay, this is the theoretical yield. In a perfect world, if nothing goes wrong, this is the maximum amount you will get from that reaction. I'm sorry I'm going fast, but I don't want to run out of time. Okay, so all you have to do now, it said in the problem that when you did this experiment, you got 33.5 grams. Well, you should have got 43.5 grams. So this is what you got, this is what you should have got. So you take this divided by this, and you get 0.77 or 77%. You got 77% of what you should have got. You lost 23% somewhere, okay? Here's another one. Okay, we got on our equation. When we start with 60 grams of water, okay, we do this reaction, and we end up with 300 grams of HNO3, which is nitric acid, okay? Now, first thing we got to do is, what should we have gotten? So we take our 60 grams, and always start with a reactant when you do theoretical, when you do percent yield, you guys. 60, 1 mole of water has a mass of 18. That's what it weighs. Then I do my mole ratio from my balanced equation. 2 and 1, 2 here, 1 here. Okay, that's where they come from. And then 1 mole of HNO3 has 63 grams. That's 1 hydrogen, 1 nitrogen, 3 oxygen added together. It's formula mass. Add those together. So 60 times 2 times 63 divided by 18, and you get 420. That's your theoretical yield. If you did everything perfect, that's the maximum amount you would get. Okay, so I'm going to take 300, because that's what it said I got, divided by 420, what I should have got. Actual divided by theoretical, so I get 71.4%. Okay, so I lost 28.6% somewhere. Okay, I didn't get all my yield. Okay, so you divide what you got by what you should have got. That's how you do percent yield. And it's a way of checking to see if you did a very good job. They do this in industry all the time. Okay, if you're only getting 50% of your product, you need to look at your reaction. Where are you losing stuff? What's going on? What's happening? Okay, so that's how they use theoretical yield. Okay, what I did on the rest of this, and I'll put it on there, there's a bunch of just problems from the chapter because we are done with the notes as far as that's concerned. So there's a whole bunch of, and I'll go through, you can look at them, and you know, it's just a review. I have another review that I'll go with you, but you can go through those if you want. But as of right now, we are done with the notes for this chapter. Whew, right? Because it took forever. Anyway, that's a limited reactant and percent yield. Okay? And again, we're done with this, plus this is the end of this unit. So make sure you get your work done.